Hi, this is homework 2 part B, in which we are trying to transform a generalized cubic equation of state to a cubic polynomial form in terms of our compressibility factor z, which here we have equal to PV over RT. So to start trying to get our cubic equation of state in terms of our compressibility factor, we are going to multiply both sides of our equation by V over RT. So here we are going to start with P. So we have PV over RT is equal to Z, and through some canceling out by multiplying V over RT here, we are left with V over V minus B minus, and then here again we have AV, and then AV here is then going to be over RT times V plus epsilon B times V plus sigma B. So from here we can further move on by trying to incorporate our compressibility factor Z into this equation more, so it's in a generalized cubic polynomial form. So in this scenario here, we are given our pressure and temperature and we are trying to find V. So from this equation we can find that V is equal to ZRT over P. So then we take this V value that we have here and we're going to plug it into these equations. But first we are going to simplify this down another step. So we have Z is equal to, and we have V over V, which we can write as 1 over 1 minus B over V. And having this V in the denominator here is nice because it will lead to further cancellation. So then we're going to write our A. So continuing on, plugging in this V value, we are going to get RT squared times 1 plus epsilon B over V times 1 plus sigma B over V. Okay, is that right? Okay, so after we simplified this down, we can now plug in the V value into our equation, and that will give us 1 over 1 minus B, and then it's going to be flipped, so it's going to be B P over Z R T, and then this is going to be minus A V over R T squared, and then this, there's another R, and then we have Z, and then this is going to be over the 1 plus epsilon B, and then it's going to be the same as over here, like flipped, EB P over ZRT times 1 plus sigma B, 1 plus sigma B over V. Continuing on from here, we can see in our equation that these three terms have BP over ZRT in common. So we can set another variable. We're going to make it beta. We're going to set beta equal to the BP over RT. And then here we also have an A over RT, and then, or that's AP over RT. Q, there's A, B, RT, and then, so it'll be Q beta over, and then we can go 1 plus sigma beta over Z times 1 plus sigma beta over Z. And that's epsilon. So continuing on, once we get our equation in this form, we can now divide both sides of this equation by Z. So this will give Z over Z is equal to 1, and then that is going to be equal to 1 over Z minus beta over Z minus Q beta over Z plus epsilon beta times our quantity Z plus sigma beta. So then, once we have our equation here, we notice that we can FOIL these out to get Z squared plus epsilon plus sigma Z, and then plus, that'll give us epsilon sigma beta squared. To continue from here, after we have distributed these two groups of functions together, we can see here that we have two denominators, or two fractions subtracting from each other, in which we need to find a common denominator. And we do that because we want to end up with a cubic polynomial in this form with C1, C2, and C3 as constants. So our common denominator is going to be Z minus beta over Z plus epsilon plus sigma times beta Z plus epsilon sigma beta squared. And so from here, we are now set with a common denominator. So I have this table set up, and we are going to fill these out with our coefficients for each of the terms that are listed above, and 1 is here for our C3, which there is no Z value. So to start, we can start multiplying these through. So we're given Z cubed, and the coefficient of that is going to be 1. And then next we are given Z times this, which is epsilon plus sigma beta, and then that's going to be minus beta. Just add that on right there. And then we have z times epsilon sigma beta. Oh, that was squared. Okay, so that gives us epsilon sigma beta squared. So now we can start with this term, and we would multiply it through the same way to solve our coefficients. And this gives us the minus b here, minus b for our z squared. And then it's also going to be minus 1. And then b times this one is going to give us negative epsilon plus sigma times beta, and that's going to be times z as well. And then next we need to continue distributing this throughout. So then we are given negative epsilon sigma, and then this one would be beta cubed. And so as we can see here, we have the beta cubed. So we know that we are then going to have minus epsilon sigma beta squared. And then we're just going, and then after we see that, get the squared, we still have our minus QB and beta, and that is on the top. So it's going to be subtracted still. So that's going to be minus Q beta times Z minus beta. And we do that because we needed to multiply it by this section of our denominator in order to combine the two. So to continue, we need to multiply this by that. And that is going to give us minus epsilon plus sigma times beta. And then same again here with this scenario. We need to add a Q beta. So we have now completed our table consisting of our different coefficients for our cubic equation of state in the form of our compressibility. So our equation here would be z cubed plus all of these coefficients, z squared, plus all of these coefficients, z, and then minus our C3, which is these coefficients. So this is our cubic equation of state in the form of our compressibility.
Hi. We are going to be continuing on with this assignment, and we're going to be writing a function to calculate the roots of a cubic polynomial. We can do that by going to collaboratory, and we can define a function, and we can go ahead and call it cubic roots A, B, and C. So once we have our function defined, we need to initialize our Q and our R values into our code. So we can set Q is equal to A, and that is squared minus 3 times b, and that is divided by 9. And our r is going to be 2 times a, and that's cubed, minus 9 times a times b plus 27 times plus 27 times c, and then that is divided by 54. Continuing on, if r and q are real and r squared is less than q cubed, then the equation has 3 real roots, and we can find them by computing theta is equal to arc cosine of r over the square root of q cubed. So we can code that using an if statement. So we have here if r squared is less than q squared, we can set theta equal to np dot arc cosine, and we make this r over, so the square root of q cubed is q to the 3 halves, and we can just type that as 1.5. So now we will be able to return the 3 roots that we would solve for in this case, that r squared is less than q cubed. So we can go ahead and return. And so first we have negative 2 times np dot square root of q times np dot cosine. And since all 3 of our roots consist of negative 2 times the square root of q times cosine of a theta value minus a over 3, we can go ahead and make it an array inside of our cosine, and we can use that in order to simplify it down some. And so we can do that by going np dot array, and then we're going to go theta over 3, and that gives us our first term. And then now we can go theta plus 2 times np dot pi, and then that is going to be divided by 3. And then our third root is going to be theta minus 2 times np dot pi over 3. Make that a little bit bigger so I can see. Okay, so now we have all 3 of our values of our cosine in an array. So I think no, we're good. So now we can just put minus a over 3. So this situation is for when there are 3 real roots. So now we're going to do this when we, so we're going to use this if we have a case in which 1 or 2 of our roots that we get are not real. So we can go else, and then we can code our a equal to negative r plus np dot square root, and inside our square root we have r squared minus q cubed. And then we need to raise this entire power, or we need to raise this entire equation to the power of 1/3. And so next we can look at our b value, in which the positive square root is assumed. We can compute for b. So we are going to say that when b is equal to 0, b is equal to 0 if a is equal to 0, and then if a is not equal to 0, we are going to put else, and that would be q over a. And then once we get our b, we can return in which the equation of the 3 roots are. So we can return a plus b capital A plus b, and then that is going to be minus a over 3. Now we are going to want to use the polynomial function in Colab or Python in order to evaluate our polynomial and to give us an equation. To show that equation, we can go np dot polynomial dot polynomial, and then we're going to go from roots, and from roots, the from roots function just helps us evaluate our roots more efficiently. So we can go ahead and input some numbers into here, and so then we can go shift enter, and then it displays our polynomial, our cubic polynomial. But for this, we're going to just set this equal to z. So now we can use the coefficients function in Python to give us our coefficients of our cubic polynomial. So we can just name this c is equal to z dot coef And then we can go Shift Enter, and we can go ahead and see what our coefficients are of the above polynomial that we created. So now that we have displayed our coefficients, we can now use the real function in Python to see when or see which coefficients we have are real. So we can go c dot real, and then we can make this range from 2 to -1. And then we have an array of our real coefficients. So lastly, we can use our cubic roots function to evaluate the cubic roots at real um, our real roots. So we can go times c dot real, and then we're just going to go with what we had above. And then this outputs our cubic root of the equation that we generated from above. This is homework 2, part B3. And we are going to be using our coefficients that we solved for in B1 for using the compressibility, which was the A and B, and the parameters for the SRK equation of state. We are going to use our cubic root calculator to determine the limits of integration for the Maxwell equal area construction, and we will estimate the vapor pressure of water at 373 kelvins and compare with the expected value. Okay, so to start, I already pulled some stuff from the previous code from the previous parts, and I've added from scipy.integrate import quad, and that is imported in so that we are able to find the limits of integration of the Maxwell area construction. So some things we need to add into here is our eccentric factor, and that is equal to 0.348 of water. And then next we need to go over here and we can set our omega value is equal to 0.0864, and our psi value is 0.42748, and we're just pulling those from this table of parameters. Next, we're going to input our B equation. So B is going to be equal to omega times R times TC divided by PC. From here, we can hit Shift Enter. So now, in our equation, we are going to define a function in order to solve our A, B, epsilon, and sigma values. And we need that in two different places. One, we need it to solve for any pressure, and then we also need it from where we found our A and B constants here in the form of compressibility. So we need those four parameters in order to solve for what we are looking for. So we can define a function and we can name it calculate A, B, E, and S of our temperature. And then, so we are going to need to be using our reduced temperature for the SRK value. So we can set TR, which is the reduced temperature, equal to temperature over the critical temperature. And then we can define our alpha equation for our SRK equation of state. So we can make alpha equal to 1 plus, we got 0.48 plus 1.574 times W minus 0.176 times W, and that W is squared. Oop. 1 plus 0.48 plus 1.574 times W minus 0.2, and then we can continue going. 1 minus the reduced temperature, and that is raised to the 0.5 power. And then we can go on the outside and then square it. So that is our alpha equation for the SRK equation of state. Next, we can introduce our epsilon value and our sigma values for the SRK. And epsilon is equal to 0, sigma is equal to 1. So once we get those coded in, we can now code in our equation for A. So we can go A is equal to psi times alpha times R squared times T squared divided by TC squared over PC. So from here we can now return A, B, E, and S. And this is solving it under the parameters of the SRK equation of state. So as we keep moving forward here, we are going to take volume and temperature, and we're going to plug it into our SRK equation of state, and we are going to output pressure. So we can define SRK P is equal to V comma T. And to be able to do this, we are going to need to pull our A, B, E, and S values from the above into this line of code. And we're going to set that equal to calc underscore ABES of T. Then we are going to return our generic cubic equation of state. So we can go R times T, and that will be over V minus B. I should probably put these in parentheses. And then we're going to be subtracting A over the quantity V plus epsilon times B, and that is going to be times V plus S, which is sigma times B. And then we hit shift enter. Okay. So now we are going to need to set up something in order to plot. So I can go back to this, and we're going to select that from part B1. And that is adding 1,000 increments of log base volumes, and it's just giving us an array, as you can see right there. So next, I'm also going to pull this so I don't have to type it all again. But you notice here we have our van der Waals equation. So instead of this, we are going to use our SRK. P. So continuing on, once we get our graph plotted, you can see here that it shows our inflection points. So our next step is we are going to go into our part B1, and we are going to pull this, and we pasted that there. Shift enter. So moving forward, we are now going to define a function that is a cubic, and we are given the pressure and temperature, so we are going to use that to then solve for the volume. So we can name that cubic underscore V. Our parameters are going to be pressure and temperature. And again, we are going to set our A, B, E, and S equal to, what did I have that name? Calc underscore A's. Calc underscore ABS of T. And if we can recall from part B1 when we were deriving the general cubic equation of state under compressibility factors, we can set beta equal to B times P over R over T. And we also used an equation Q is equal to A over B times R times T. So now that we have our beta and Q equations that we use to help us evaluate the cubic equation of state, we can now use our cubic roots function on our coefficients for the cubic equation of state and the compressibility state. which was the set of values in the table for z cubed, z squared, z, and 1. And I have this pulled up here just so I can reference it and not have to turn around every time. So now we have z's equals cubic roots, and we have 3 cubic roots. So then we are going to have E epsilon plus sigma, and that is going to be times beta minus beta minus 1. So that is our first root that we are going to solve. And then next we are going to have epsilon times sigma times beta, which is squared. And then that is going to be minus epsilon plus sigma times beta squared, and then minus epsilon plus sigma times beta, and then we are going to add q times beta. So that is our second. And lastly, we're moving on to our C3. And then, so we can begin with minus epsilon times sigma times beta cubed minus epsilon times sigma times beta squared, and lastly minus q times beta squared. Let me get out of these brackets. Okay, so now we have all of our cubic roots typed in to our z's cubic roots. So now we are wanting to return our volume roots. So we can return our z's times r times t divided by p. So now that we have returned our cubic roots, we now want to determine the limits of integration for the Maxwell area construction and estimate the vapor pressure of water at 373 degrees Kelvin and compare with the expected value. So from here we can define Maxwell area. I'm just going to label it Maxwell P, comma, T. So moving forward, we have VL, VM, and VG, and that is equal to cubic underscore V of P of T. So now what we want to do here is return, and we're return our function, and we are going to use this quad function here and lambda to evaluate our integral, and hopefully we're able to find the area under the curve, and then that value should be the vapor pressure at the temperature we're looking for. So we can return, and here we are going to use our quad function. Quad. And then we do lambda to evaluate at the integral of the functions that we are looking at. So we have lambda v, and our parameters are going to be pressure minus our SRK P V of T, and we're going to use that array of our volumes and temperatures to use this. And our rest of our parameters are going to be VL, VM. And then we're going to have set a 0. And on the other side of our equation here, we are going to again have quad lambda v. And this time, instead of taking P minus our SRK, we are going to take SRK P of our volume and temperature minus our pressure. And our parameters for this one are going to be VM and VG. And then once again, brackets 0. Shift enter. Okay, so now we can take a guess with pressure to see what we get. So we can take Maxwell 91 e to the 391,000, and then for our pressure and our temperature over here we have 373 Kelvin. Shift enter. So using the parameters that we set above here to solve our definite integral, you can see here that I wasn't really able to completely get it. Every time I tried 373, I kept getting a unpack error that I could not solve. So thank you. Hope you enjoyed my video.